Dr. Kim, can you hear me?
Yes, I can hear.
Yeah. Please start your presentation, doctor.
Okay. Thanks, Chairman. Good afternoon, ladies and gentlemen. I am Young-Hoon Kim, a member of Professor Park's group in Yonsei University in Seoul, Korea. It is my great honor to give a keynote presentation at this meeting on behalf of Professor Park about the work of nanoporous aerogel materials in Yonsei University. Professor Park asked me to convey his approach for not being able to give a presentation due to an urgent personal stage, and to transfer sincere his thanks to the symposium chairs and organizing members. So today's presentation topic is nanoporous materials, synthesis and application studies of aerogels. The nanoporous materials, such as aerogels, have large specific surface areas and pore volumes due to their high porosity, and exhibit small values for apparent density, diffractive index, and thermal conductivity. From this, light transmission or surface functionalization can be maximized, and heat or sound transmission can be minimized. So it can be applied as thermal insulation, drug delivery and catalyst, filter and sensor, and batteries, and low-K, and thermoelectric, and so on. The aerogel, a representative nanoporous material. It has an open cell structure and can achieve a porosity of up to 99%, and the specific surface area over 1,500 meters square per gram. The size of the primary particles forming the network structure is around 3 nanometers, and the pore size is around 10 nanometers. For a better understanding, the specific surface area of 10 grams of aerogel are equivalent with the size of a football field. In addition, although it is an open cell structure, it exhibits very excellent thermal insulation properties, as you can see due to the small nanosite pores. The aerogel have unique and useful properties such as low density, low heat conductivity, and sound transmission due to high porosity. But its mechanical properties are very poor due to the very small fraction of solids forming the external structure. Compared to regular silica, it can be seen that silica aerogel exhibits small mechanical property values equivalent about 1,000. Therefore, the support material or structure control is required to enhance strength of structure. This slide is about the history of aerogel. The aerogels were first introduced in 1931 by Dr. Kistler, and it was first commercialized in 1940. But due to high cost of drying method, it was difficult to commercialize. Since 2000, the economical ambient pressure drying method was developed, and the mass production of aerogel has progressed since then. The Aspen Aerogel and Cabot Corporation could manufacture various types of aerogel, such as powder, monolith, blanket, and so on. Since 2010, the multi-compositional aerogel have been researched for enhancing the mechanical and other properties. This slide shows the general synthesis process of aerogel using silica aerogel as an example, and it called as Jorgel process. The precursor solution forms a colloidal Jor, then changes to hydrogel through a gelling process, and then a wet gel is formed through an aging process. Then drying step is progressed. If only the solvent is well removed through drying without shrinkage, it becomes an aerogel. But if shrinkage occurs during drying due to the capillary force of the solvent, aerogel is formed. In order to control the pore structure parameters, such as porosity, pore size, and primary particle size of the aerogel, it is necessary to properly select and control the parameters. From this slide, I'm going to present the synthesis and application of various types of aerogels investigated at Yonsei University. Synthesis of this type of aerogels have been mainly studied and their application to absorption, superinsulation, low-K, gas sensor are researched. So now I am going to introduce why we research to give functionality in aerogel. This is about the enhancement transparency. Interest in improving the optical transmission of silica aerogels lead to the synthesis of aerogels using a two-step Jorgel process. To process optical transparent silica aerogel, the ammonium fluoride and hydrochloric acid were used as hydrolyzing and condensation catalyst. The degree of transparency in two-step Jorgel process-based aerogels is higher than the conventional single-step aerogel as shown at the photos. The two-step Jorgel-based aerogels have a large surface areas with small and uniform pores, and it can contribute to high transparency of aerogels. The enhanced pore structure results in high transparency of aerogels. If you look at the photo of the two-stage base aerogel presented at the bottom, the upper side photo is about the one-step base aerogel. Then you can see how transparent this two-stage base aerogel coating window is compared to the case of one-stage base aerogel presented at the top. This slide is about the controlling the surface group of aerogel. The aerogel can be made as hydrophobic or hydrophilic through surface modification. Originally, the aerogel has hydrophilic nature due to many hydroxyl groups onto the surface, and it can show selective moisture absorption capability as shown in this video at the top side. In this study, the surface of aerogel has been modified with methyl groups, which shows extreme hydrophobicity. This modification could be confirmed through IR analysis. As you can see the video at the bottom side, the water drumlet remains on the top surface of aerogel due to the hydrophobicity. The aerogel has highly porous structure, so it can easily absorb external material. Depending on the surface characteristic of the internal pores, it is possible to selectively absorb water or oil. The video on the top, it can show that the hydrophobic aerogel selectively absorbs only oil from water and oil mixture. The aerogel that has absorbed oil in this way can release the oil by compression by hand, as shown at the right side of photos. And it was observed that the shape of the aerogel and the ability to absorb oil do not change even if the absorption and release are repeated dozens of times. An aerogel can be used for filtering of waste oil as shown in the photo at the bottom side, and we can get clean oil for recycle. This slide is about the application research, low-K dielectric material. As we know, a low dielectric constant material for an intermetal dielectric is evitable to reduce power dissipation, crosstalk, and interconnection delay in the deep submicron device design. It corresponds to the successful fabrication of silica aerogel film for an application to low dielectric material. The highly porous aerogel material was synthesized with 1.6 nanometer pore size. The same image at the top, it shows excellent gap filling capability of silica aerogel films. Through an incorporation with organic linker, an enhancement of mechanical properties of aerogel films could be confirmed by nano-indentation measurement, such as around 2 gigapascal of Young's modulus. As you can see this current voltage data, the silica aerogel film shows just around 10 nanoampere current with an applied voltage at 10 volts and over 6 megavolts of breakdown. These are acceptable and compatible values with currently applied materials for intermetal dielectrics. More surprisingly, the dielectric constant of 1.45 was obtained. Furthermore, semiconductor processing adaptability was proved. As you can see, the silica aerogel film showed a good sideward angle behavior during drying etching step, and also a good planarization behavior after chemical mechanical polishing process. In this study, the tin oxide aerogels with different texture structures were obtained for applying to anode materials in lithium-ion batteries. This study revealed a relationship between the pore structure and cyclability as anode material. The prepared metal oxide aerogels with smaller pore sizes and larger specific surface areas showed greatly improved cycling stability in lithium-ion battery. Due to a suitable pore properties, it can enhance the cycling stability. The enhanced carbon monoxide gas sensing properties of titanium aerogel were investigated. As we can see, the highest porous sample with the largest surface area showed the highest sensitivity. Pore size of tin oxide aerogel samples were controlled using the variation of additive water amount for hydrolysis reaction to reveal the relationship between pore structure and gas sensitivity. As we can see in the figure, the carbon monoxide gas sensitivity of tin oxide aerogel was enhanced with increasing water content. That is to say, as increasing the water content, the pore structure was maintained well. In this study, a homogeneous dispersion of graphene oxide flakes in a tin oxide precursor solution results in a formation of uniform nanocomposite. The chemical interaction between tin oxide aerogel matrix and graphene oxide functional groups was confirmed. The photocatalytic activity of these nanocomposites in the material range degradation was found to be accelerated through the compositization. The photocatalytic degradation characteristics of silica and titanium composite aerogel was also studied by using methylene blue dye. At this system, titanium acts as photocatalyst in the composite, whereas the silica construct three-dimensional nanoporous network. From this slide, I'm going to explain the methodology for enhancing the mechanical properties of aerogel. It is mostly related with composite aerogels. As we know, a weak mechanical properties of aerogel are the most important issue, and this brittle nature limits the application of aerogels. The left top video clearly shows a weak mechanical properties of aerogel. When we press the aerogel very weakly, we can see the aerogel is broken into powder immediately. But through the bonding network modification of aerogel, the silica aerogel can be made flexible. At the right side video, when we compress the aerogel with a stick deeply, we can see that the aerogel can recover its original height and shape. It can be explained that the flexible nature can be induced by repulsive force of methyl groups at the surface of pores. And we investigated the effect of silica nanoparticle addition to silica aerogels on the mechanical and thermal properties of the resultant aerogels. In this study, an hydrolyzed surface treatment of silica nanoparticles was firstly adopted to increase the number of chemical bonds with silica aerogel during the condensation reaction of the silica aerogels. An increase of particle size of the silica aerogels was observed with enhanced mechanical strength and thermal resistance. This result indicates that the introduction of silica nanoparticles with surface hydroxyl groups into silica gel is a feasible way to control the synthesis of nanocomposite. In this study, surface-treated multi-wall CNT by presulfonation was used as reinforcement to improve the mechanical properties of silica aerogel. The results show that inserting small amount of multi-wall CNT in the gears caused enhancing the dimensional stability and mechanical strength of silica aerogel. As a result, the modulus enhanced 10 times than pristine aerogel. From the same image, it was confirmed that the silica aerogel primary particles kept on the multi-wall CNT from the condensation reaction between the hydroxyl groups of multi-wall CNT and silica aerogels. The upper part of the slide, it shows the preparation of silica polymer composite aerogel by high internal phase immersion process followed by gel process. The silica aerogels were grown in the scaffold of macroporous flexible polymer monolith to overcome the brittle nature of silica aerogels. This composite monolith possesses extreme properties such as high flexibility, elasticity, superhydrophobicity, low density, and low thermal conductivity. This novel way of preparation allows us to overcome the fragile nature of silica aerogels while maintaining textural, physical, and functional properties. We synthesized porous polyhype networks with Schlaner functionalities in the polyhype backbone. These Schlaner functionalities are used for covalent bonding with silica aerogels embedded in the polyhype. The covalent bonding between silica and polyhype networks resulted from an introduction of chemical linker. The silica aerogels covalently bonded with polyhype network. It shows macroporous and mesoporous morphologies. The polyhype silica aerogel nanocomposite possess excellent properties like high bendability, high elasticity, superhydrophobicity, and so on. At the right video, we can see the oil absorption capability of polyhype silica aerogel nanocomposite materials. And from the TGA profiles, it showed that the polyhype silica aerogel nanocomposite materials have high thermal stability up to 300 degrees Celsius. The materials have a good cycling stability for various kinds of organic liquids, including petrol and crude oil. In this study, the silica aerogel was formed onto a polypropylene scaffold using a two-step Jurgel process. A great enhancement of the mechanical properties of polypropylene silica aerogel nanocomposite was obtained. This novel approach of incorporating silica aerogel onto polypropylene shows great potential as a durable superhydrophobic and corrosion-resistant thermo-insulating materials. As the conclusion of this presentation, I present in this slide about the possible application of the aerogels in near future from the unique and distinguished properties of aerogels. As you can see, it can be applied to construction, aerospace, energy plants, and heavy chemical industry from thermal chemical resistance and lightweight properties. In addition, it can be applied to the electrical and electronic industries from thermal, dielectric, and isolation properties, and to the chemical industry from thermal, chemical resistance, and absorption properties. Furthermore, it can be applied to fields such as biomedical, automobile, and telecommunications from thermal chemical resistance and lightweight properties. In this way, the aerogels are materials that have endless possibilities. In order to overcome the limitation of aerogel and develop aerogel as a general purpose material such as next generation plastic material, the Korean government established this aerogel material research center at Yonsei University, and the various domestic universities and foreign research institutes and industries are participated in this center. And the Professor Park would like to thank the Korean government for providing the foundation for research on aerogels through the establishment of this center. The Aerogel Materials Research Center is open to all researchers interested in aerogels. So please feel free to contact us at any time to discuss common interests. Thank you for your attention.
Thank you for that insightful speech, Doctor. The stage is open for questions now. We assume there are no questions for you as of now. Thank you once again for the speech, Doctor.